All right, so hello everybody. Welcome to week 2 of classes and week 2 of DeepRob. So hopefully the rest of your classes are going well. It's great to see so many faces here in person, and it's good to see people online too. So today's lecture is going to be on image classification. So a note on the slides, the slide file is really big. I did not anticipate it being half of a gigabyte, so GitHub doesn't want me to upload half a gigabyte to our website. So after the lecture, I'll figure out how to upload the slides so that everybody can have them. And the recording will also go up later today. All right, so for today's lecture, the topic is really coming from the standpoint of really it's a building block of the perception that our robots are going to need. So the high level idea is that our robots, many of them have cameras attached to them, which can take images. And we want to know what is in the image so that the robot can start to act on what the environment state is. And so to give a sort of like a motivating example of this, actually I forgot, administrative updates. So a few things before we get into the more exciting stuff of image classification. So first, Project Zero, released last week after right before our first lecture. The instructions are on the website under the projects page. The due date is this coming Thursday at midnight. So if you haven't started yet, I'd suggest getting started, because working with Colab, or if you're going to develop locally, can take a little bit of getting used to and some time. So I would definitely try to start if you haven't yet. The autograder's up. People have been asking some good questions in the forum, which is good. And so this project is really an introduction to PyTorch, like we talked about at last discussion. So if you want to rewatch the discussion, that recording is up on the website on the calendar. And so that's some Project Zero. One thing to note that's very important for Project Zero, there's a small typo in the notebook where it says that we're using PyTorch version 1.10.0. That's a typo. We're actually using 1.13.0, which is the same as what's on Colab. So if you're using Colab, there's nothing to worry about here. But if you're developing locally, a few people have had issues with the GPU portion of the code producing essentially different results than the CPU version. I think especially it's on Mac. If you have like an M1 chip, the PyTorch version 1.10 has a bug. If you update to 1.13.0, as far as the core staff is concerned, we think that fixes the issue and that the matrix multiply function should work. But if you're having issues with that or worried about it, come to office hours or post on the forum. Two other quick notes or sort of suggestions on the project is make sure that you save your notebook file before you upload the submission to AutoGrader. It's tempting to think that it auto-saves, because sometimes it does, but when you get to the very end, it usually doesn't. And then finally, to avoid usage limits, especially as we get close to a deadline, I'd suggest closing your tabs when you're falling asleep and don't leave them open all night. Other administrative topics, I think just 2 more slides. So one, if you want to join the discussion forum, it's good for asking questions on the projects or lecture. It's opt-in based because we're going to be interacting with students from other universities. So there's a Google form. The link will be embedded on these slides, but also it's on the website on the syllabus. And if you fill out the Google form, we'll add you to the forum. The final administrative update is on enrollment. So we issued an additional set of roughly, I think, 20 class permissions just based on the max occupancy of the room it should have been yesterday. So if you haven't received a class permission, I'd say after lecture, let me and Professor Jenkins know, and we can work through that. Okay, let me know, and I'll work through it. But okay, so before we get on to the topic of image classification, I'll pause and see if there's any administrative questions that are broadly available. Is everybody accessing the resources, like the website and that?
Have you started Project Zero? There we go.
Okay, nice.
All right.
That's good. And that reminds me, actually, there's one other resource which, so the website you should be able to access, the autograder, the project. The one thing that we've been getting questions about is the grade scope. We haven't set up the Gradescope course with the roster yet. So if you're not in the Gradescope course, or you try to go to the Gradescope link on the page and it says that the course doesn't exist or you're not in the course, that's okay. We're going to upload the roster to that tonight or tomorrow. So lecture on Thursday, I'll have an update about that. You can expect the quizzes to start next week during lectures. So the way that'll work is we'll post the link during lecture, so you can see the link during lecture, and then we'll give you very ample time. So I'll talk more about the specifics of the quizzes on Thursday. Okay.
You have a question in the chat.
Question in the chat. All right, so can we have extra attempts on AutoGrader? I feel like 2 is too low in my opinion, especially for other projects. Okay, so it's very early in the semester to start like extending projects. There were some questions at office hours about like extending Project Zero. The reason I'm hesitant to extend Project Zero, I'll answer that first, and then I'll get to this specific question, is that Project Zero is very light compared to what's coming up. And so I think to stay kind of on schedule, it would be good if we could stick to the original deadline of Project Zero. If you have extenuating circumstances, like you were traveling and you got backlogged and you weren't back in Ann Arbor and things by the first few lectures, I think we can work with you. And then in terms of the AutoGrader, I think for now we're going to keep it at 2. And then if the feeling among the class is that it's too high, that we all need more, then we want to be reasonable. The reason for having 2 though is just to kind of the same reason why there's grading. It's a forcing function to make us all improve ourselves essentially. So so for now we're going to keep it at 2, but come to office hours if you're concerned about that, and we can make some considerations. What's the reason for having a daily limit? The reason we're having a daily limit, it's a good question. So to some extent it's philosophical, right? So one part of being a good developer, whether it's for machine learning or anything else in software or robotics, is you want to test your own code. Because essentially, when you go into industry, someone is going to be giving you money or some other resource in exchange for code that's functional. And it's going to be your job as a developer or a manager of a project to ensure that the code that you're producing and putting out into the world is actually functional. So in the real world, there's not going to be an AutoGrader. And so having a limit on the access to the AutoGrader here is a way of still giving you feedback, so you can still have some sense of that you're improving, but at the same time, it's a way to encourage you to test your code locally. So that's the reason for having a daily limit. Chad, anything you want to add in terms of philosophy for AutoGraders?
Sure. I want to say a little bit. I believe this is the AutoGrader policy, correct me if I'm wrong, standard practice on campus. But also, I would echo that you should do your own tests to make sure that they work. We also have limited ability. We could very easily crash a lot of our systems if we had unlimited attempts. So we prefer that you work with this limit. If you have any questions or you want any help with the projects, you can always come to office hours, and we're happy to walk you through it.
Mm-hmm. Yeah, and in terms of, and I guess one more administrative update, and then we can get into classification. Office hours, the schedule is posted on the homepage of the website or the staff section. So we have office hours at least for 1 hour every single day of the week. You can join via Zoom. It's the same link as lecture schedule. And so the exact time is up on the website. The rooms are it's the second floor conference room and the third floor conference room in this building, if you want to join in person. Okay, image classification. So image classification is a very fundamental task for perception. And so camera sensors nowadays are very, very cheap. It's very, very easy to take images. And our robots need to understand what's in the world. And one way that they can try to do that is to understand what's in an image that they could sense. And so this topic of image classification is really a core task within the field of computer vision. And so robotic perception is borrowing from all the work that's been done in computer vision to try and enable our robots to start to take action in the world after they perform some of these classification tasks. So to give an example of what it is we might want a robot to do, I really like chocolate-covered pretzels as a snack. And so one long-term goal for our robots, especially the work that we do in the Laboratory for Progress, is to try and have personal assistance robots. So things that could operate within a domestic environment to serve tasks that you might be interested in. So let's say, for example, that I'm working here late as a grad student and I'm hungry. One potential request that I would like to make to our fetch robots is for it to go downstairs to Icon Cafe and bring me back chocolate-covered pretzels. And so if it's going to be able to do that, one of the sensing actions that it's going to have to be able to do successfully is to observe the products or the food that's in the Icon Cafe and decide which item is the chocolate pretzels. So in this case, let's say that the robot has taken this input image and it wants to decide out of a fixed set of possible categories what is in this image, right? So maybe it's chocolate pretzels, but the Icon Cafe also serves granola bars, potato chips, water bottles, all sorts of other food items. And so the goal of image classification is to just perform this function, to take in a single image input and produce a discrete category label that would go along with what is the subject of the image. And so what makes this really challenging for our computers to actually do is what we refer to as the semantic gap. And so what we mean by that is that for us humans, it's very, very easy. It's extremely natural to see images, to see basically pixels on a screen, and to interpret them with really high-level information based on all the knowledge that we've learned and all the biological properties that our brains have, right? So we see that image on the left, and we instantly recognize it as food. What the computer sees when it sees the image on the left is an array of numbers. It's a big three-dimensional grid of just integer numbers between 0 and 255. And so it has to try to take that extremely low-level signal of just a grid of numbers and interpret it as a very high-level class. And so that's very difficult to achieve. In addition, another challenge that our systems have in the real world, in the physical world, is that as the viewpoint of our images changes, the low-level signals change drastically. So for example, if the robot is to rotate around this subject, the entire grid of images, or the entire grid of pixels, is actually going to correspondingly change. And it can change it very, very drastically, even with a subtle change in viewpoint orientation. So even though the subject in all of these three images remains the exact same, right? It's still chocolate-covered pretzels. The underlying matrix of numbers that our algorithm is going to be exposed to can be completely different. And so trying to encode how it is an algorithm should take these very, very drastically different arrays of numbers and produce the same output with a correct class label is a real challenge. Another challenge we have is that within this category of chocolate-covered pretzels, there's not just one like, let's say, product that would fit into that category, right? You can have all sorts of different types of chocolate-covered pretzels. So we might want our algorithms to understand that all three of these that we were showing in this particular slide would serve the purpose of providing me the item that I'm wanting, even though each three of these products has extremely different packaging and different features that go along with it. So we might want, actually, for our robot to be able to pick out a specific one of these, right? So we might want very fine-grained classification in addition to like higher-level classification, right? So that's going to add another layer of difficulty for our algorithms to overcome. Moreover, in the real world, we're not going to always get those close-up photos right on the subject. We're going to have images that are very, very cluttered, where there's multiple items in the image. There's potentially occlusions. There's potentially issues with image resolution. So for example, if you take a photo with an iPhone 14, you're going to get very high-resolution photos in comparison to what you might get from, let's say, a sensor that's on the Fetch robot, the Asus RGBD camera. And so all of these are going to result in essentially differences in the input distribution that our algorithms have to overcome. Another one, just to kind of add even more difficulty to the mix, is illumination changes, right? So we want our robots to be able to operate in the same environments that we do. And we operate all day long, right? So we operate in bright environments, dark environments, environments that have a lot of reflection. And this introduces yet another challenge, because in each of these, let's say, different illumination images, the object within it is still the item that I'm wanting. But the pixel values that are within this span of images, once again, are totally different. Yet another challenge that we don't sort of think about in our daily lives might be subject deformation, right? So these objects are actually deformable. They can change their shape, but they still remain the same class. So we want our vision algorithms to be able to overcome that. Another one, which I kind of mentioned earlier, was occlusion. So we want our robots to be able to sort through occlusion, right? Our world's not always organized. It's not like a warehouse. There's a lot of mess that our robots have to sort through. And as part of that, our perception algorithms also have to sort through it and understand that what is actually within the environment. And then yet another one, which sometimes, which we see frequently in robotics, but sometimes is not addressed as much in pure vision, is that we have to remember that our robots are ultimately going to have to take some action. So sometimes it's not enough to just classify from an object standpoint what is in a scene, but we also need to understand the semantics between objects within the scene and how that's going to relate to the actions that our robot can take. So for example, in the case of the left, there's a mirror that's reflecting the pixel values, or the sort of the intensity of light that's reflecting off of the object of interest. So from a vision standpoint, there are sort of two chocolate-covered pretzel bags. From the standpoint of a robot, it could destroy itself, right, if it tries to act on the mirror and not on the and not on the actual bag. In addition, for acting on, let's say, the bag of pretzels, if it's kind of skewered by this shelf, is yet another semantic relationship that we might want to classify in addition to just what the actual object is, because we need to act on it after we've done some perception. And so together, all of these challenges and even more that I haven't gone over here are what makes this task really, really difficult to implement in practice. But if we could implement this in practice, the applications of image classification are really broad. So outside of robotics, image classification has been used in all sorts of ways. So one pretty exciting one is within medical imaging. You can train classification models on X-ray data, for example, to detect the types of tumors that might be present or not present within patients. Astronomers, for example, have collected data sets of galaxies to try and identify them. If they produce, like, let's say, some new satellite that's going to go into space, you might want to detect, localize and detect where the known galaxies are from different vantage points. Within robotics, also, there's all sorts of image classification applications beyond just that chocolate pretzel example. So the paper on the left was looking at trying to detect, trying to classify what direction a trail moves from the perspective of a drone. And on the right, there was an interesting paper looking at trying to classify the level of ripeness for tomatoes in a harvesting robot. So and this is just a very, very small select set of examples that I've picked out here. It's a very powerful technique, and one that is not limited to just these discrete labels. But what you can actually do with it is you can use image classification as a building block for more complex perception tasks. So for example, let's stick with this setup of having my fetch robot go and grab me a snack. One way that you could use image classification to perform a higher level task, a more complex task, is by using a set of, let's say, sliding windows across the image, and then actually classifying every single sliding window into some class. And so this is what we refer to as image detection. So what we're doing is we're actually taking every possible sort of subgroup of pixels in the image and trying to decide whether it fits into a class. And if it does, then what we've essentially done is localize not just what is in that image, but where that image is within the overall scene. So image detection is going to be one of the projects that we look at coming up. But using image classification in that sliding window approach is one way that we could build up to that higher level perception task. So to sort of visualize what that looks like in a sliding window, we could imagine, let's say we pick out some crop from the original image, and we could then classify just the crop. So in this case, we've picked out the sign at the upper portion of the image, and we've decided, based on our classification algorithm, that that is a picture of a sign. We could then sort of just slide that crop to some other portion of the image and reclassify that portion of the image to now detect maybe snacks in that segment of the image that's below the sign. And so now we're having this localization information, right, where these classes are in addition to what the classes are. Right? So if we keep sliding down, I'd then detect the fetch, and you could kind of keep going throughout the image for all these different windows. Another example of how image classification can be a building block for other tasks. Yes. All right. So the question is, can robots use their embodiment to enhance object recognition, e.g., knowing how to get a better look, or does current technology just observe static images? Okay, that's an exciting question. So that's an open area of research. So that would fall under active perception is one word for that. So essentially deciding how I should act to change what information I need to sense to accomplish some task. So potentially, like in this cluttered example, the robot might first detect, oh, there are many, many objects here, and maybe I don't have enough pixels on the target object, so I want to move closer. So that'd be an example of active perception, or as you called it, like kind of an embodiment of your artificial intelligence, right? So your AI system might know that it exists as a form of a robot, and I can then choose to act to change what I'm sensing to serve some task. So yeah, it's a very interesting area of research. We can definitely talk about it as the semester goes on. So, all right, so image classification, so we can use it for object detection, right? So we can localize where within these images objects are with the sliding window. In addition, what we can do is we can use image classification also in that sliding window fashion to build up what we would call a pose estimation approach. So let's say that we take a sliding window and we take a crop out of the image. What we could then do is we could build another model on top of just this crop of this known class that would specialize in detecting the position and the orientation of the known object type within that crop. And so knowing the position and the orientation is what we call pose within robotics. So what we might want to do is know, like, for example, the 3D position in space, and then let's say like a quaternion about the orientation of this pretzel bag. And knowing the pose then would let our robot ultimately move its gripper to that location and then take an action on the object. So we're going to be building up throughout this semester, starting with image classification in project 1, then up to object detection, and ultimately all of us are going to do a pose estimation project in a similar fashion to what I just described. So given that image classification has this power, right, it's this like very fundamental approach, the next thing that we have to do is actually implement an image classification algorithm. And at first, when you actually sit down to your IDE or your Google Colab, that can be very daunting, right? So let's say you set up a function definition that's going to be your image classifier. The next thing you have to do is somehow write down code, right, that's going to compile and is also going to be able to handle all of those issues that we talked about, from the viewpoint variation to the interclass variation to the illumination changes, all of those things, right? Because ultimately you want your code to work in the real world. And so this is a very, very different type of problem than what you might have encountered in pure programming classes, right? It's not as well defined as what you would do for sorting a list or for doing like a matrix multiply. There's a defined input and an output, but how it is you're going to process the input into the output is a black box. And so that's what makes it a really interesting problem to try and tackle as an AI developer. So one approach that you might try and use is sort of to use like an older school, we could say, version of computer vision. So you might take your image and extract some sort of higher level features than pixel values, right? So maybe edges, but they're still very low level within the scope of classification. So you might, let's say, run like a canny edge detector and produce like this second image in the scene. From there, then you could maybe detect corners, right? Like Harris corner detection algorithm to try and decide like which pixels in the image are the corners of the bag. And from there, you could hopefully maybe decide, okay, well, based on the size of the area within the corners, that might correspond to the Hershey's bag versus a different bag. The challenge, though, is that might work for detecting the bag if it's in like a very confined environment, or it's just that one bag that you're looking at. But if you try to extend it now to work on water bottles or to work on chip bags, the features are going to be totally different. So you might have to redesign all the work that you did on kind of handcrafting the decision on how a corner would relate to the class for every single type of class that you want to encounter. And so this is this one approach that you could take, but it's going to be very difficult to generalize to all the sorts of objects that exist in the wild that we want our robots to interact with. So instead, the approach which is now certainly the most predominant within image classification is to use a machine learning approach. And a machine learning approach is fundamentally data-driven. So what we mean by data-driven is you go into the world, you collect a large training set of images and corresponding labels for each image. You then use a machine learning algorithm, which is well-defined, to train a classifier from that data, and then you would evaluate how well your classifier performs on new images from the wild that you've never seen during training. And at that point, if you're confident with the performance on these new images, you could then deploy a robot and have it go and find the chocolate pretzel bag for you. So to give an example of one training set that we're going to be working with in this semester, if you look on the right-hand side of the figure, there's this image of kind of household objects. This is ultimately what we're going to be working on with starting in Project 1. And so I'll talk a little bit more about it today during lecture, and also the discussion on Friday is going to be focused on this data set. So within the machine learning framework, the way that we're going to approach kind of implementing our image classifiers is now going to be broken up into two separate functions. So instead of having that one black box, which we would have to fill up, we now have two. We're going to have a training function, which is where we're going to try and use that set of images and labels to teach our machine learning algorithm. And then we're going to have a predict function, which is going to be used at runtime when you actually deploy it on the robot, which is going to take in some image with an unknown label and just produce a label. So in terms of what data sets exist so far to support these machine learning algorithms, there are many image classification data sets. So one that you will see referenced quite frequently is this data set MNIST. So this is a pure computer vision, I would say, data set where you have binary images that are 28 pixels by 28 pixels. They're corresponding to human handwritten digits from 0 to 9. And so the goal is to classify sort of one of those image chips into the corresponding digit that the human was intending to write. Yep. So when is it better to train specific classes, such as mustard bottle, versus generalities such as bottle with a subcategory of mustard? Okay, yeah, that's very interesting. So there's a distinction, like when we were talking about with that interclass variation, between what you might call instance level classification versus usually what's referred to as category level classification. So an instance might be the Hershey's cookies and cream chocolate covered pretzel bag, whereas the a category level might just be pretzel bag or even just food bag, right? So you could keep going higher and higher level. Ultimately, the choice on where you pick your categories is going to be up to the specific end user of your robot. So if you want your robot to be operating with knowledge of a mustard bottle specifically, you'll want to collect your data set and your labels that will include mustard bottle. On the other hand, if your robot and the end user does not care whether it's mustard or whether it's ketchup or whether it's any other form of liquid that can go into a bottle, maybe you just collect a data set of many types of bottles that are all called bottle, and you ignore that lower level information. So ultimately, it's really up to the end case. It's up to the sort of end user and what their needs are. On the research side, we want to try and answer all of the hard problems. So doing category level estimation can sometimes be more challenging. And so, because sometimes what you can do is you can use like the low level knowledge of the instances to sort of help your algorithms. But we'll see that as we go along. Thanks for the question. Let me pause. I've been kind of going for a bit. Just any questions so far? Okay. So in terms of the size, so MNIST, believe it or not, is actually a relatively small size data set in the grand scheme of things. So 50,000 training images, 10,000 test images. And because of its small size compared to other classification data sets, it's fairly rare to expect, if you have outstanding performance on MNIST, that doesn't necessarily mean that your algorithm is going to have outstanding performance on a more complex data set. Typically, you will want to work, you might use MNIST for proof of concept, just very quick, because you can fit it on, let's say, even potentially a CPU, you could fit a model to train on MNIST. But then when you try and move to a more complex data set, you should probably expect your performance to drop in terms of accuracy of classifying. So a slightly more complicated example, which is used more frequently, I would say, is Cyfar 10. So this is 10. So there's 10 classes. So you can see in this figure the 10 classes that exist within the data set. They're slightly larger in size, but they're still pretty small. So 32 by 32, this time color images instead of just binary. And then it's the same overall number. So you have 50,000 training images and 10,000 test images. So because now we're working with color, and also because the classes here come from sort of natural environments, you see a lot more variation. And so that's where the complexity comes in. So you start to get some of those issues with category level classification. For example, if we look at the row of, let's say, deer, these are pretty, there's quite a bit of variance, right? The color of the deer is changing, the illumination within the images is changing. So some of those more challenging aspects of classification start to come up in Cyfar 10. There's another variant from the same authors, which is Cyfar 100. You usually see this used a little bit less, but you'll still see it. Instead of having 10 classes, you have 100 classes that you're trying to classify. Otherwise, though, it's the same size of the images and number of test images. So the most common classification data set, which you'll see referenced in literature, is ImageNet. And so this is one that you will see very, very frequently referenced, both for pure classification tasks and also for the building blocks that we talked about. You can use ImageNet to sort of support those more complex perception challenges. So the breakdown of ImageNet is you have 1,000 classes 1.3 million total training images, and then 50,000 validation images, which you can use for proving your algorithms locally. And then finally, 100,000 test images, which are actually kept secret. So you won't actually know what the test images are that your algorithm is being run on. These images are were primarily extracted from the internet, so they're of varying size themselves. They're not all the same square shape like in Cypher 10 and Cypher 100. But usually what you'll see done in literature is the algorithms will first resize the images to a fixed dimension, for example, 256 by 256 pixels before training. And there's a challenge for ImageNet. So typically what's done is to actually establish what the performance is, they measure what's called top 5 accuracy. So instead of expecting your algorithm to produce just one category as a final prediction, your algorithm could sort of propose 5 possible categories, and then you would just measure whether or not the correct single category is represented in those top 5. And so that's called top 5 accuracy if you look at some of the benchmark performance on the ImageNet challenge. So in addition, though, we're not limited within image classification to just objects. You could also imagine classifying scenes or places. So the MIT Places dataset is one that supports different kind of environments that you might want to classify. So you can imagine this being useful within robotics if we have a robot that might have to operate within, let's say, both cafeterias, like here at the robotics building, within elevators, like we also have here at the robotics building, but even, let's say, at home, right? So it might have to go across these different environments and know what environment it is at any given instance. So a data set like this could support your robot in actually being able to classify those different places. This is even larger than ImageNet, so you have 8 million total training images. Once again, a lot of the images come from the internet, so that you typically will resize them to ensure that there's a fixed input for your algorithms in terms of size. And what we're going to be working with on the projects in this data set in this class is a data set that comes from our lab. So we have this data set which we're calling the PROPS data set, which stands for the Progress Robot Object Perception Samples data set. And it's going to be structured in the same way that Cypher 10 is structured overall. So we have 10 classes that we're going to be working with. They're of typical household food items. So there's like a coffee can, which is the Master Chef can, cracker box, so like a Cheez-It box, sugar box, tomato soup can, mustard bottle. These things that you would expect to see in like a kitchen environment of a home. So overall, so that we have those 10 classes. They're each going to be 32 by 32 color images, and then 50,000 total training images and 10,000 total test images. And so with this data set, this is going to start to get us thinking about what types of objects and classification problems our robots would want to be able to solve. And so all the algorithms that we work on are going to be built on this data set, but you could extend the algorithms to those other data sets that we talked about just with potential modifications. In terms of overall size, to get a sense of the size of these data sets, we could ask how many training pixels in total each one has. So the y-axis here is on a log scale. So every bump up is going to be an order of magnitude increase. So you can see that from MNIST up to Cypher 10, Cypher 100, and the props data set, there's like almost an order of magnitude increase. And then moving to ImageNet, there's a 2 order of magnitude increase in the total number of pixels that we can use to train. So that huge increase in available data for training is part of what makes ImageNet so much more commonly used in literature for training these models. It gives a much more complex problem to solve, but also a much larger data set to actually try and solve the problem with. And then finally, yeah, the places data set is even yet another order of magnitude larger than ImageNet. One kind of interesting thing to note, so within research, one of the trends that has been happening in the past few years is actually trying to use less and less data for classification problems, but also all sorts of other machine learning-based projects, because collecting all of this data or labeling all of this data is extremely expensive, right? So like a couple of grad students, very unlikely could label 1.6 trillion pixels worth of categories, right? Like you could hire teams, right? You could hire like many people to label that, but that has a very high cost. So if we have some new application or some new environment that we want to put our robots into, what we might want is not a huge data set that we would need to first collect before training our algorithms. Instead, what we might want are algorithms that could use a very small amount of data and still work. So one thing that's worth thinking about as we go along in the semester is how maybe you could make some of the algorithms that you see achieve the same performance or better performance, but using less data, because that's a very valuable aspect of for improving these algorithms. Okay, so given these set of classification data sets that we might want to work with and that we will be working with, let's now talk about how it is we're going to implement our first classifier. And so if we go back to how we said the machine learning framework was set up, we have to implement these two functions. First, a training function, where we're going to use our images and labels to actually teach the machine learning algorithm, and then a predict function, where we're going to actually try and have our machine learning model produce a new label for an unseen image. So in the case of the nearest neighbor algorithm, which is our first model, the training function, all it's going to do is memorize exactly all of the training images and all the training labels that we're giving to it. The predict function, on the other hand, is going to try and predict the label according to the most similar training image that we saw during training. So that, at the highest level, that's what our goal is going to be for writing code that actually implements this train function and this predict function. So in order to do that, what we first have to, or like one of the things that we're going to need is we're going to have to decide for some given new image at test time for the predict function, how do we measure its similarity to those training images? And so one approach that we can use to measure similarity between images is using a very low-level measure like the L1 distance, sometimes called the Manhattan distance. So what this distance metric does is we take our two images, we then treat them as that array of numbers, and we take the absolute difference, element-wise, between every pixel within, let's say, the test image and then every pixel within the corresponding training image, to produce ultimately like these absolute differences at every pixel location, and then finally take a summation over the full array of pixel differences to produce a final numerical score for distance. So this is one approach that we can use to implement the distance metric, and it's what we'll use on project 1 for our nearest neighbor algorithm. So given that we're going to choose that distance metric and we want to implement those two functions of train and predict, we could then look at what this classifier actually looks like in code. So on this one screenshot here is a full implementation of a nearest neighbor classifier. So if we step through it, the first thing we can do is we can look at the train function, and we can see what it's doing. So we're giving it input X, which is our images, and Y, which is our training labels, and all we're doing is memorizing, right? We're just storing in memory those same images and those same labels. At test time then, once we want to go and predict a label for a new image, we have this for loop, which is just going to go over every single test image that we want to predict a label for. We're going to compute, I don't have line numbers, but we're going to compute on the first like non-commented line, kind of where my cursor is highlighting down here, the distance between this particular test image and all of the training images that we have. We're then going to record which of the training images had the lowest distance to this test image and report or predict the label for that corresponding closest image in the training set. And that is going to be our overall classifier. So a question then that might come up first is, if we have, let's say, n total examples during training, so n images and n labels, how fast is training? So the answer is already on the screen, but the answer here we're going to say is constant time, O of 1. What we're going to assume for that answer is that like we're just storing the pointer to the same images. We're not going to duplicate the images, but it's constant time. So that's very, very fast for training an algorithm, right? It takes essentially no time. It doesn't matter how big your data set is. This classifier will take the same amount of time for training on, let's say, Classifier as it will take for training on ImageNet. The next question, though, that we want to ask is, and this is the more important question in all likelihood, with, let's say, n examples for a test time, how fast is it going to take to predict a label on all n of those examples? And in this case, actually, it should be n training examples, let's say. So the answer is to predict a label for now a single test image is O of n, right? Because we have to compute the distance between this one test image and all n of our training images that we saw during training time. The reason that that's a problem is that as we increase the size of our training set, that means our robot's going to be slower and slower when it's actually deployed. So really what we want is the exact opposite of this. We want to have our predict function be much faster, right, orders of magnitude faster than our training function, because we can afford offline training, right? So you can offload training to like AWS or Google Cloud, but on the robot itself, you might not be able to afford that. You might not have access to networking. You might not have a GPU on the robot or a server of GPUs on the robot. And so we want our predict functions to be very fast. So typically the nearest neighbor classifier, while it's useful for getting a sense of the machine learning framework, and it can be effective in certain use cases, this high cost associated with the predict function is going to be a limiting factor for it. So it's a problem. Having said that, there are approaches. So there's been a lot of work done to actually try and improve the speed of nearest neighbors classification. There's just one example linked here on the slide. But if you're ever in a case where you absolutely need nearest neighbors, there are some approaches, and it is an interesting area to look at how you can improve the speed performance. For example, there's like approximate approaches. But so you can check those out if you're interested. Okay, so let's say now that we've implemented this classifier that we saw in the past few slides, let's try and understand, let's get some intuition for how it actually is going to be for performing. So what I'm showing here on the left-hand column, so this is my implementation of the k-nearest neighbors classifier. On the left column, there's a set of test images. So these are images that were not seen during training from our props data set. And on the right then, for every test image, which is a row, there's then 10 columns corresponding to the 10 nearest neighbors in kind of from most similar on the left to less similar on the right. And so what we can do is we can try and kind of understand first like the accuracy of our predictions. If we were to say pick the most similar neighbor, which would be in the first column of the square image, and we can try and understand how accurate is our model. So in this case, it's not too bad. I think we get 60% from this sample correct. But there are some that are very hard to explain, right? So even like the first image, that test image, which is of a Cheez-It box, the most similar image from the training set apparently is of this is an expo marker, a black expo marker, kind of like this one. And so it's kind of hard to explain why it is that that's the most similar on a high level, but in terms of pixel values, apparently that's the most similar training image that we have to the Cheez-It box. Some of them, though, are quite good, right? So like then the second example, so at the second row, the coffee can actually is correct, and most of the nearest neighbors are also of the same coffee can. So this gives us some sense of kind of some intuition of what to expect from our nearest neighbors, right? So there are going to be some that are visually similar, but then there's going to be others that where they're actually not quite similar at all. And part of it is also going to have issues of like, if we have a lot of occlusion in our data set, for example, like this second to last row here, this is a highly occluded image. You actually can't, this is actually an expo marker that it's supposed to be predicting, but it's hardly visible at all. And so that is going to be a real challenge for the nearest neighbors, because essentially all the pixel features that are visible, or most of them, don't actually correspond to the object that we're trying to classify. So when you take those pixel-wise differences, they're somewhat meaningless at the highest level. It's also interesting to look then at how this nearest neighbors algorithm would perform for natural images, because in natural images, for example, these are images taken from Classifier 10, we have a lot more intra-class variation. So in our props data set, it's all instance level, right? There's only one coffee can. In Classifier 10, there's not a single frog. There are many frogs. So what you can see, for example, if you were to apply your algorithm on Classifier 10, what you could expect to see is it might actually still perform it might perform roughly the same, maybe like around 50% accuracy you'd expect, maybe slightly better. But because the inter-class variation is very large, there's going to be some cases where like the background can have a huge effect, right? So it's using maybe in this frog case more the fact that the background is white than it is using the fact that the frog has very different features from a cat, which seems to be predicting as the nearest neighbor. So doing some of these analyses can be good for building some intuition about the algorithm, and we'll have a chance to do that in Project 1. Okay, let me pause and see. I'll go back a slide. Any questions so far? Any thoughts on viewing some of these examples from the k-nearest neighbors output? Not seeing any. Okay. So one way to sort of introspect and ask how k-nearest neighbors performs is what we were doing there. So you'd visualize the predictions that the algorithm performs. So you can use that same approach on the future algorithms that we're going to talk about, right? So you can use like a sort of qualitative output from its predictions. In addition, though, for k-nearest neighbors, one thing that we can do is we can visualize the actual decision boundaries in a visual format. So what we're showing here is an example of if we were to imagine that we had images that had only 2 pixels, so we could call it like pixel 0, which we'll say has a value that's like a sliding scale along the x-axis here, and then let's say pixel 1, which has a sliding scale along this vertical axis. We could visualize the performance of k-nearest neighbors in terms of its decision boundaries within this 2-dimensional space and try to build some intuition about how k-nearest neighbors performs and what characteristics it has as an algorithm. So within this figure, the points, the actual circles that are shown within the shaded areas, those are the training samples that we used during the memorization phase, the training phase of the algorithm. The actual background colors then that are highlighted, those represent areas of this image space, this 2-pixel image space, that would be classified according to a particular one of the classes, where each class is a different color, if the image were to fall in that region. So for example, where this red X is in the lower left portion of the figure, if that were to be a test image, we would classify according to this model it as being from the red class because it falls within the portion of the region that is red. And its nearest neighbor would correspondingly be this red point, which is kind of highlighted like by that dashed line. So the decision boundary then, which we're referring to, represents the actual portion of the space where there's a change from one classification to the next. And so these decision boundaries within k-nearest neighbors, they can be very noisy depending on the training data that we're using. So these highlighted regions here in these black circles are pointing out portions of the space where you change drastically just based on one training point from, let's say, being like from the green class to the blue class. And so because our training data can sometimes be noisy, our model's predictions can correspondingly be noisy. And so one question that will come up is how could we potentially smooth some of these decision boundaries? And the answer is to use more neighbors, right? And so the reason that we might want to smooth them is, once again, the fact that it's possible that in the labeling process or in the data collection process, maybe this green point wasn't really corresponding to the green class, right? Like maybe one of our labelers made a human error. Or alternatively, maybe it's like a very niche case that we wouldn't expect to see frequently, but we just happened to when we collected our training data. It might actually be worth calling that portion of space blue instead of green to try and smooth out our overall performance and maybe make it better. And so to do that, we can use additional neighbors. So in moving from, let's say, the nearest neighbor classifier to the k-nearest neighbors classifier, what we can do is we can base our predictions not just on a single nearest neighbor, but instead we can treat it as a majority vote. So at every portion of the space, we'll try to find what are the k nearest neighbors to this portion of space, and whichever class has the most votes is going to be classified accordingly. So this, for example, is a plot showing the same training data, but if we, instead of basing our predictions with one neighbor, if we instead base them on the majority of our 3 nearest neighbors. And so you can see that in this case, the decision boundaries are much smoother, right? So we don't have as many portions of space that are sort of like sticking out at those single training point instances, which are highlighted here. So using more neighbors helps to reduce the effect of outliers from our training set. The one challenge, though, that comes up potentially is that we have ambiguous portions of space now that we have to deal with. So if k is greater than 1, it's possible that there could be ties during the voting process. And so those are the portions of space on the right-hand figure that are colored white. So we would have to somehow decide how to break a tie to still produce a prediction for an image that falls into those portions of the space. So for k-nearest neighbors, we earlier were looking at the L1, the Manhattan distance for computing similarity or distance. that's not the only choice that we could use. So instead of L1, we could use, let's say, Euclidean distance. So in Euclidean distance, instead of treating the overall image as just like this grid of pixels where we're going to take the sum of the absolute difference at every pixel location, you can think about using an L2 distance as flattening the image into just a vector, and then computing the actual Euclidean distance in that high-dimensional vector space. And that could be a distance metric that you use. But you could even go and use other metrics. And commonly in research, you'll actually see some other interesting metrics, which I'll bring up towards the end of the discussion. So to visualize, for example, how the performance of k-nearest neighbors would change if you use different metrics, there's this plot here. One thing that's kind of interesting is it actually turns out that the geometric properties of the decision boundary can be informed by which distance metric you use. So if you're using Manhattan distance, it actually turns out that you could expect the decision boundaries to always fall along essentially like axis aligned, so either like 90-degree or 45-degree angles, whereas in Euclidean distance, it's still piecewise linear, but not necessarily following those same properties. So understanding how your distance metric will affect performance along the decision boundaries is another way that we can try and understand how the algorithm performs and maybe tune the algorithm using different distance metrics. And so one kind of like interesting point, but we're not going to spend too much time on this, is just to think about the fact that if you can define a distance metric for a particular data set, you could apply k-nearest neighbors. So we're talking about images, and we're going to, for the rest of the discussion, we're going to stick with images. But if you had some other sensory data, let's say audio data, or you had maybe like LiDAR data, if you could define a distance metric for that input data, you could still apply k-nearest neighbors. So it's worth thinking about. The other thing I'll point out, so the instructor, Justin Johnson, who had taught a version of this course previously here, and also was one of the instructors for the CS231 class at Stanford, he developed this really, really cool online demo of k-nearest neighbors. So the plots that were generated for in this lecture so far come from this demo. It's still online, so I'd recommend checking it out. The link will be in the slides. You can see it written here. It lets you play with essentially like different training points, different numbers of training points, how that affects the decision boundaries, if you were to use L1 versus L2 metric. So you can build some intuition about how this algorithm performs visually using this demo. All right, so given that we have this algorithm defined, one of the things we saw towards the end is if we move from being just the nearest neighbor with k equals 1 to now k nearest neighbors where k is, let's say, equal to 3 or maybe even 4 or 5, that value of k now could affect our performance, right? So we got different decision boundaries based on the choice of k. And the natural question then to ask is, well, which value of k would produce the highest accuracy on the data that I expect the model to perform on, right? Because we want to pick the best. In addition, we saw how if we pick different distance metrics, the different distance metrics can impact the decision boundaries and correspondingly impact the performance. So we want to know how we could potentially pick what distance metric to use to achieve the best performance. These are referred to as hyperparameters. And so in a general sense, hyperparameters will continually come up for every single machine learning model that we look at throughout the course of the semester. And so how we define hyperparameters is it's the choices that go into a particular learning algorithm that are not learned from data. They're the choices that the human engineer or the human researcher is sort of implicitly building into the model, not based on training data, but based on their decisions. And so they're not learned, in other words. So these hyperparameters and how you choose the hyperparameters, they can vary from data to data, from task to task, from domain to domain. And so this makes it a real question about how it is we actually should pick these hyperparameters, which we're going to have to do ultimately to get an implementation working. And so in general, there's not a single rule that you can use to always pick the best hyperparameters. It is itself a search problem. So typically what's done is you try many hyperparameters, and then you pick the model that performed the best. And you pick the hyperparameters that went with that highest performing model. So let's consider ways in which we could potentially pick our hyperparameters using this sort of trial and error approach. So let's say that we have our data set. So the way to understand this figure is essentially like this data set, you can think about like the percentage of training images that we have as like along the horizontal axis. one way that we could potentially decide on how we want to pick our hyperparameters is to just train the model on the full data set and then evaluate that same model on the full data set with different hyperparameters and pick the hyperparameters that perform the best. But this is a totally wrong approach to try and pick hyperparameters, right? So as a very clear example why, let's think about for k-nearest neighbors what this would do at test time. So if we were going to test our k-nearest neighbors algorithm with k = 1 on the same data that it was trained on, it just memorized the training data, right? So at test time, when we give it, let's say, image 1 from our test set, it's going to go and find image 1 from the training set and say, oh, this is the most similar. Its label is, the blue class. So it's going to end up with a perfect accuracy. It's going to predict every single class correctly because all it did was memorize the training set and then sort of regurgitate the training set back. And so that is just a very that's kind of like a trivial example of how testing your algorithms on the same data that you train them with is a bad approach to establish their real performance, right? Because if you were to take that k = 1 model and then evaluate it on new unseen data, it's very unlikely that you would actually expect it to achieve 100% in the wild. So what we want when we're trying to decide on our hyperparameters is to actually get a real good measurement of how they should be expected to perform in the wild. So a better approach might be to split our full data set into a training set and a test set, where we use just the training set to actually train the model, and then we evaluate it on the test set a single time to decide on what we would expect to see performance once we deploy the model in the real world. And so the issue here, though, is that we don't necessarily, let's say, know how the idea or how the algorithm is going to work on new data if we're using this test set during our development to pick the best hyperparameters. And so typically what you should see done is instead break your training set into, let's say, your data set into 3 different bins. First, you'll have a training set. You'll have then a separate validation set, which you can use to tune your hyperparameters. And then finally, to get your final measure of what you would expect the performance to be once you release it into the wild, you'd have a small portion of the data set, which is a test set, which has not been seen at all when you were picking hyperparameters. But then you evaluate your final model on one time, and that's what you would report as your expected accuracy. And so this is a way of basically trying to establish how well your model should be expected to perform once it's actually deployed. So from there, though, this would potentially be considered sort of like one-fold validation, where we have broken our training set up into this one fold over the overall data set. You could go further, though, and you could sort of imagine breaking that training portion of the data into multiple folds, and then iteratively going through each fold, training on a portion of the folds and using the held out single fold as like a validation set, and then averaging your performance over the different folds where you're doing this training as a maybe slightly better measure of how your final performance is going to be in the wild. And what this is sort of doing is it's allowing you to tune your hyperparameters on slightly different, on these slightly different subsets of your total training set, and get hopefully a better performance, or like hopefully better prediction of how the model will perform in the wild. The downside with doing this k-fold validation is that it requires you to train your model many, many times, right? So depending on how many folds you pick, you're gonna have to train your model a whole time for that fold. And so if you have a very expensive algorithm, that can be prohibitive. But as a sort of golden rule, this would be like the ideal way to get a measure of how your model performs. But in practice, what you'll more frequently see is a single validation set, a single training set, and then the held out test set, which you would only ever run on one time. Okay, so we're gonna use k-fold cross-validation in Project 1 for our classifiers. And what we'll expect to see is going to be a plot like this. And really, anytime you use k-fold validation, you could probably expect to see a plot similar to this. So on the vertical axis is the accuracy. And then on the x-axis is the particular hyperparameter that we're trying to tune. So for k-nearest neighbors, the x-axis here would be, let's say, k. And so within each of these, at every choice of k then, we have a separate data point for the model's accuracy on a single fold from our validation set. And if we then averaged the accuracy for, let's say, like the 5 folds that we're using in this case, the line plot then is showing the average over the 5 folds of our model's accuracy. So based on this, what we can do is we can then look at the line plot and try and find, well, what's the highest average accuracy over the folds, and choose the hyperparameter that corresponds to that highest average accuracy. So in this case, right around k equals 7 is where we see the highest averaged k-fold accuracy. So we would try and then, use our k equals 7 model as our final best performing model that we want to put on the robot. So this is what we'll be using in project 1 to pick our hyperparameters. Okay, so an interesting aspect of k-nearest neighbors is that it's a universal approximation function. So what that means is that as you keep adding an infinite number of training samples, your nearest neighbor classifier actually can represent any function. So there's a caveat in that from like a pure mathematical standpoint, there's like a lot of sort of technical details that we're kind of glossing over, but from our applied side, like kind of viewpoint, what this really means is that as we increase the number of training samples, we could expect our models to get better and better. And so one way that we could visualize this then is we could actually try training a model on an increasing number of samples in some like one-dimensional space and trying to understand how it performs. So let's say that we have this true function, which is the blue line, and we're going to use the input label x to then try and predict like an output label y. That's what our classifier is going to try and do. The green line here is showing the classes that would be assigned based on the k-nearest neighbors using the corresponding 5 training points. If we increase that to 10 training points, you can see that our green line is approaching the blue line. And once again, if we go to 20, it gets better and better. It gets closer and closer to that true function. So this is just sort of an intuitive way to understand how this universal approximation property of k-nearest neighbors holds. But for like a more technical, from a more technical or like theoretical standpoint, we'd have to look to like real analysis and things like that to try and actually prove that out. So we're not going to worry about the proof in this class. Okay, so given this very nice property of k-nearest neighbors that we could in theory evaluate we could in theory approximate any function, the problem that we're going to run into is what's called the cursive dimensionality. And we see this come up over and over within artificial intelligence. What the cursive dimensionality says is that if you have some space and you want to have uniform coverage of it, the number of samples that you would need from that space to keep the same density grows with the dimensionality of the space. So let's say, for example, we're in a one-dimensional space and we have a density of 4 points within this space. If we were then to move to a two-dimensional space, we would need to square the number of points to keep the same density of samples. And then once again, we would need to then cube the number of points if we instead went to 3 dimensions. And so this increase in the number of points that we need to cover the space is what is going to hold back k-nearest neighbors from truly ever being realized as a universal approximator, because we're never going to be able to have an infinite number of samples that covers every possible image. So another reason, like kind of another reason why k-nearest neighbors is held back is that evaluating distance on raw pixels can have its own issues. So in particular, we have to deal with that semantic gap, right? So if we're working with raw pixel values, we're ignoring high-level concepts. So to give like kind of just like a qualitative example of that, so in the 3 images on the right-hand portion of this figure that are all modified versions of the original, those all have the same distance metric to the original. So from the k-nearest neighbor standpoint, like you can even like remove portions of a human's face and it would still be just as similar as just a shifted version of the image in color space. So once again, this is sort of an issue with k-nearest neighbors of trying to deal with that semantic gap from low level to high level. Having said that though, k-nearest neighbors can be quite useful. So potentially instead of working on raw pixel values, what we could do is we could use k-nearest neighbors to work on the features that are learned from some other machine learning algorithm like a convolutional neural network. And so this is a practice that is actually used somewhat frequently, and it works really pretty well. So the examples from this paper are showing the k-nearest neighbors, if you were to evaluate them based on the higher level features from a learned image classification network. And so you can see that it's fairly robust to changes in like viewpoint variation, changes to like occlusion, changes to the pose of the subject. So like, for example, like the trains here, right? The orientation of the trains changes in these nearest neighbors, and yet the the classifier is still able to find those as being related. So k-nearest neighbors does have some nice properties that we can use it for. So in summary, we're running kind of low on time here. So we looked at image classification, and at a high level in image classification, we start with a training set of images and labels, and we then have to predict one label for each image within a test set. The challenges we saw with performing image classification were quite numerous. So at a high level, we have this semantic gap that we have to try and deal with, right? So going from low-level pixels to high-level classification. But in addition, we had issues of trying to produce models that were invariant to occlusions, to sensor variation, to illumination, and that can be a real challenge to actually implement. Having said that, even though it's a challenge, it's a worthwhile challenge because we have these other tasks like detection and pose estimation that could really benefit from having a strong image classifier. And so the first one that we looked at today was then the k-nearest neighbors classifier, which requires a distance metric and some hyperparameter k to actually implement. And finally then we looked at how choosing those hyperparameters can be done using a validation set. And importantly, we'll only ever evaluate our model's performance on a single held out test set a single time to actually establish what its performance was. So on project one, we're going to get experience with all of these topics that we talked about today. And next lecture, which is on Thursday, is going to be on linear classifiers. And that'll be the second portion of project one. So after Thursday, we'll have all the kind of course lecture content material that you'll need to actually implement project one. Having said that, project one will be released also on Thursday, and we'll talk about an intro to project one and also the data set that we're using during discussion this week.